So my name is Adil, and I've been working at Dropbox for the past year, mainly working on the backend, like key value store, building key value stores, measuring performance here and there, writing out some multi-homing components, but mainly Go, all the components in Go. Dropbox use pretty big use of Go. All of their backends are written mainly in Go. So I'm a pretty big user of Go. In today's talk, I'm not going to talk about any of the games, as my friend earlier talked about. It's going to be overview of how you can use different tools that are available with Go toolchain, toolchain to debug or analyze or step through the different or the performance issues. And then I'm going to dive into a live session where I'm going to take one program. I'm going to show you how can you debug, how can you find CPU or memory issues with that problem, and how can you drill down and find what was causing that application to slow down. Okay, why do we need performance? Why do we need to care about performance? Well, you can test your application as much as you can in your stage environment or in your desktop or wherever you want, but you're gonna hit the limits, or your performance is gonna bite you really hard when you push the code in production. That's where the things go south. So, and to be ready for that, you wanna make sure you are measuring all the key metrics properly. So, for example, average doesn't make sense. So, for those of you who are focusing on measuring latencies in terms of average, you should not do that, because that doesn't tell you what the 1% or the 5% of the customers are seeing or are experiencing. So we really want to make sure that you are measuring your performance in terms of percentiles, and P99 or P95 or P90 is what you should look at. And those are the percentile ranks where you would see GC coming in. P99 is usually where GC pauses you would see. Yeah, Go, like Java, is also a garbage collected language, and you should be very careful in using allocating objects in the heap. Okay, what is profiling? So profiling, in lame words, it's looking at in pretty lame words, you are pausing a process, looking at what the stack is, and then trying to make sense of what is CPU working on right now on this thread or on this Go routine in terms of Go. So if you do that multiple times in a second, what you get is that you get a list of stack traces, or you get a list of stack traces. Now with that stack trace, what you can do is that you can do interesting things. You could generate a call graph, or you can see where your CPU is spending most of the time, because if you see a function appearing at top of the stack multiple times, that is a function which is taking more time. So you could do a lot of these interesting things, like build call graph, how many times one function appears in the call graph in the call stack of another function. So let's see. How can we? How many of you have seen this kind of a snapshot before? Okay, pretty much. A lot of people have seen that. But anyway, I'm gonna still go through and walk you through this graph. So this is the output of a profiler snapshot. What you do is that you run the profiler on a program that is done for 60 seconds. It would generate a profiler log, and that profiler log you can use to generate this PNG or PDF or image. What this image is showing you is that the way to read it is that each node is specifically a function. And for example, in this case, there's a node called find loops. So find loop is a method inside Go application. And it took like 35.32 seconds in total in this method. And 4.41 second is the time that this method took. All the other time, which is like 30 seconds, was spent on calling or waiting on other functions to process or complete. Does it make sense so far? Okay. So Go was built primarily for backend services. And for that reason, I think it has a very nice set of tools to do the tracing, to the profiling, looking at the memory, looking at the GC time. It all comes out of the box. You don't need to, for example, find a URKit for Java kind of thing. Everything is there out of the box. So what can you profile? So you can profile a standard application, a standard application. You can start the application with profiler flag turned on. When the application shuts down, you would see a profiler log file that you can use to analyze. Or you could also profile a live process. So this gives you a greater flexibility in debugging, let's say, production issues. Let's say you found like one machine which is taking too much time to serve a request, and at that point you don't want to shut down that process. Or you can take a live snapshot of that process, and the way to do that is that use this http.pprof. It's very easy. I think it's pretty easy to include that. I think I already mentioned that what we can do with profiling data. Let's skip over. With Go, you could do a couple of type of profiling. You could do CPU, and you could do memory profiling. CPU will essentially let you know what functions, at every pause, what functions were on the stack and how much time they were taking to execute. And memory profile essentially lets you see how many memory allocations are happening in each function. With Go, one of the other nice thing is that I think some other languages do that too, like Java and stuff. You can annotate this data, this profiler data, along with the code. So it gives you a very nice view to be able to drill down. When writing unit tests, you could write unit tests, but another thing I think is less known feature of Go is the benchmarking. The same unit test or same test that you're written, you could append that with the benchmark keyword, and then what you can do is that the interesting thing you can do with that is that you can see how much time that specific function you are testing is taking. So this benchmarking framework will run this for like 20,000 times. It will give you the average time it took, the method took. And another thing it shows you is that how much of allocations or the buffers that method allocated in each run. And you can also do other things like you can play with the multiple CPUs, one CPU, 2, 3, all those kind of things. Okay, so while doing a live demo, I thought about that. What should I present here? So I have a lot of examples from my production code, but I don't want to show you how that works out. So I went ahead and found another problem, another set of problems, another set of code. So this code is called finding loop. This is I don't know if you guys are familiar with that. So this algorithm is used to find loops in a code that compiler uses. It was written some time ago. You can look at it. There's a paper out for that. But this algorithm uses some of the advanced structures like union set, deep recursion, and so what I wanted to do there is that I wanted to show you this method, show you this process, and walk you through how we can profile this find loop algorithm in Go. Okay. Could you see that now? Okay, let me increase a bit more. How about now? So the way to extract or run a process with the that would produce CPU profile is that you pass in an argument, and that would let the system know that we are enabling the profiling now for this process. So this command will execute and produce a CPU profile for me for this program. And what I'm going to do with that is that I'm going to show you how we can look at this profile. So Go has this tool called bprof. If you can highlight that program for you. So what I'm doing is that I'm calling that program and passing him my original program, and along with the profiler log that I extracted. And when this program is running, I could type some commands like top. So top will show me what were the functions that took most of the time during the execution of 60 seconds or 50 seconds. So as you can see, I could see that there's the way to read here is that, like for example, this map access method, it took like 5.8 seconds. That's how many time this method was on the top of the stack. And so on this, on like fourth column, fourth and fifth column are how many times, let's say, find loops appeared in the call stack. So it's like 61% times find loops would have appeared in the call stack. Do you guys follow that? Okay, so let's try to see what. Okay, what else can we do with this tool? What we can do is that we can type in web command, and it will show me the call graphs. Okay, so this is similar to what I showed you earlier in my talk. Sorry. So I wanted to highlight this section which says 50 seconds or 52 seconds. That's how much time this process. Could you? Yeah. That's how much time this total profile trace took to execute. And if we look at a little bit more carefully, we can see that in the find loops program, we are spending 2.4 second amount of time while accessing maps. So if we do, so let's try to clutter this out. We can focus on specific areas of this call graph. We can say, hey, just only show me calls which make, only show me functions which made call to maps. Let's do that. So this is the same code, same snapshot, but now it's much more cleaner. Now you can see that the find loops is the main method, which is calling the hash map lookup, and another method which is calling hash map lookup is main.dfs. So let's try to see so we can drill down into find loops source code to see what's going on there. So list method allows you to drill down into any method and annotate the code along with the time it took to execute individual line. Let me go all the way to the top first. Okay. So this method took a total of 4.8 seconds. That's what it is showing, individually showing you what each line, how many times each line took to execute in cumulative in total. And what we see here is that if you look at this line, that's where the map access is coming from. This is where we're generating the map. That's why it is taking 2.8 seconds. And down below, if you look here, there. Yes, here. This is where we are populating the map. Sorry. So you don't need to worry about what this code is doing and what it's not doing. So what the point I'm trying to make is that the use of map here is not really needed at this point. We could use a list to represent this map. So the moment I replace this with list, you will see that we'll get significant gains, and we'll get the runtime will come down from by 0.75x. How do I erase I wanted to show you the code changes that we made, but I think it's pretty small. But anyway, bear with me. Trust me that we replaced that mapping function with the list. The moment we do that, then you would see that the speed has gone on quite a lot. So this is the first iteration of the method. It took like 52 seconds, 52 user seconds. And the moment we replaced this code, have like one with two, where we took the map out and we are using list, it's now taking 33 seconds instead of 52 seconds. So I'll show you what happened there. I'll show you what else can we do there. So now let's look at the second iteration of the program. So I don't know if you guys remember, but let me scroll back a little bit up. So when we issued top command in the first iteration, we saw that the map assigned was high in the list, map access and assign. So now let's see where does it stand now. Yes, nowhere to be seen here now. I think it's pretty much down in the list. but now we see another kind of problem. We see that we're doing a lot of GC now. It's not because of that. It's not because we removed map. It's because we are unrolling or uncovering more problems now. What we can do is that we can look at that. We can see what's going on there. So let's try to do a little bit more deeper here. Sorry. So we see that we're allocating objects from all different places, but we don't really know how much data we are allocating from these different methods, with the functions. So what we can do is that we can now start working toward getting the memory profile. Let's try to get the memory profile and see if we can add some more data to this snapshot. So I already ran this program, computed the memory profile. I'm going to run it here now. So top shows me find loops. The main method is taking 21 megabyte out of 45 megabyte total used by this execution, the whole process. So we can drill down, we can see what exactly is find loops doing here. So here you can see that we are allocating 4 megabytes of data on this line, and a couple of megabytes here too, which is the same as this is the same variable backpreds and this non-backpreds. What we from the if you're looking at the code, we know that we are using this map for one purpose only, and the purpose is to make sure we don't insert duplicate items. We're using map in replacement of a set. That is why, but we don't know. We could get around that. We can have another method that could mimic the functionality of a list. So what we can do is that we can have a list, and while inserting element into the list, we can check to make sure if the element already exists or not, and then insert it to it. So hopefully that should give us some gain. Let's try to see if we can get some gain from there. Let's see. By the way, there's a whole lot of initialization happening here if you guys see here. So in the next iteration, what we did was this code was further updated to remove the map and replace that with the pseudo set. Because Go doesn't have a what is it called? Set data structure. So what the code did was iterate over the list, create a slice, and iterate over a slice before inserting to verify whether that element exists there or not, only that inserted. So let's see what we get with that gain. So now we see that malloc GC is gone from this list. We don't have, okay, we have less thing to, we have worry about malloc, but we have more thing to worry about some other things. Let's see what else can we do here.
So the total memory usage went up from 40 something to 50.
Yes, because we are, I think in this case, we are not, let me think. Okay, yeah, in case of maps, you are basically allocating and deallocating the objects quite a lot. But in case of the list, it's pretty cheap. I'm not sure why the memory utilization went up. It could be dependent on the how frequently the GC is running, but the CPU overall CPU time came down because we are doing less and less map lookups now. So one thing I forgot to show you is that let me try to pull up the last profiler. I'll come back to it. Let me pull the last profiler log first. So there's a command called WebList. What it does is that it opens up a browser. What you can do there is that you can it's a pretty nice view where you can look at, like, let's say, find loops method. Yeah, here, and then you can actually look at the assembly here as well, like where here. If you expand it, you could see the all the details, like runtime calling the map assign function. So this is pretty cool, this WebList feature. And this is all out of the box. There is no extra tool or thing I have to install separately. Coming. So I think that's pretty much it for this session. I think what I can do further is that I can show you a little bit more detail about my setup. So I used on my Mac, I used a Linux virtual machine where I ran all the tests there. Then copied the profilers on my Mac so I could drill down the details. I can show you all the details here. Let's come back to the main presentation now. At this point, do you have any questions on the profiler running or commands that are typed? But yes, go ahead.
Is it safe to run the profiler on production servers?
The question is it safe to run profiler on production servers? There will be certain extra latency introduced because this profiler will pass the process 100 times a second. But I've seen that in production, you will start timing out some requests, but the server will not crash, hopefully. So I think it's safe. I've done that in production, so it works. The question is, how can you attach a live process? So Go provides this very nice API called pprof. So all you just need to do is that include these 3 lines in your source code, and then, or maybe 5 lines in your source code. And after doing that, your application will start listening on some port. This is essentially a web server. your application also serves as a web server, then you can start sending commands like generating CPU profiler, or you can execute. You can take live dump from this Go pprof tool, command line tool, or you can do the web. You can use interesting details from web UI.
How do you do the profiling with Seago?
So Seago is tricky because the moment you, so this question is that how do you profile unmanaged code, right? How do you look at the performance of the code that was not necessarily written in Go? So I've seen that in past. I don't think Go provides you any details to see what's going on in that process. It treats it as a black box, like a function, like a black box function. So I don't think there's any way you can Go can shed more light into what's going on in the process.
Can you use the tool to get any insight into like the garbage collector itself? For example, it's the way that it's collecting the garbage and then it's exchanging the garbage with the next.
So the question is it possible to attach debugger to a garbage collector process? I am not sure. I have not done that. But I think, but what you want to do is that you want to see how the GC is performing at any given point of time. Go provides these nice set of command line variables, command line arguments that you can pass in to enable tracing, GC tracing. Java also does that similar thing. So you can enable GC tracing to see at what time and for how long your program was paused. And how long was it paused? Was it stop the world? Was it concurrent GC? And how many memory was allocated or deallocated or freed during that time? But I don't think you can attach profiler to Go's GC.
So there's an argument to be drawn for that you can ask for allocated objects, not in-use objects. So it profiles all objects that have been allocated, even if they are gone already, so that you can kind of see at least the things that are going into GC, you can kind of see using bigger objects.
Is it that in use? I have that. Let me show you that.
Versus a lock or something like that, which is more allocated.
So if you pass in-use objects to your memory profiler, you could see how many times was that object allocated during the lifetime of the program. So let's see. So now instead of showing, now in this memory profile, instead of showing how much memory this line contributed to, it's now showing how many times this object was allocated. So this is interesting to know that another tool chain in your pocket to see what type of objects are we allocating. So I have some more slides to cover. Let's see how we're doing time. So when you talk about GC, two things come to your mind. When do you do garbage collection? And when you do garbage collection, is it going to stop the process? In other words, it's also called stop the world. Before Go 1.5, it was mainly stop the world garbage collector. So every once in a while, depending on how your heap size is growing, if the heap is growing faster, the Go runtime would stop the world, pause your process, essentially, look at your variables and see which ones are not referenced and try to claim them. So this would not work very well for applications which are sensitive to low latency. But with Go 1.5, Go came with Go was released with concurrent GC. So that means every time stop the world event happens, it would not take more than 10 milliseconds to finish. So this caused latencies to improve quite a lot. You can see experiments. There were experiments run there, and also if you are for some reason at Go 1.3, I would strongly encourage you to use 1.6, and you'll start seeing latency improvements. So when talking about performance tuning, specifically GC performance tuning, Go's stance is very different from other GC languages. In short, like in Java world, if you are to tune a garbage collector, there are like so many parameters. You could use CMS, you could use parallel GC, you could use a young GC, so all kinds of things. So there are many options that you can use to tune a Java garbage collector. But when it comes to Go, there's only one parameter that you can tune, which is Go GC. I think the main reason for that was the simplicity and not having to spend hours and hours trying to tune what GC works well for your application. Instead of, I think what they believe is that incoming iterations, the runtime will become intelligent enough to pick the right parameters for you. So you don't have to worry about these parameters. That's the reason. So what Go GC does is that it gives you the application some time to how frequently you want to pause the process, or how frequently you want to GC to come in and do the garbage collection. So 100% is the default value. The more higher it goes, that means you're letting the runtime know that it's okay for the heap to grow, let's say 2x for 200%. So you're trading off more memory and getting back the performance basically. I think for today's scenario it works very well because memory and the CPU are cheaper, so you can set it to maybe 200 to start with. So there's another parameter called GC trace. You can pass it along your command line, and every time a GC happens, I think I'll talk about that, but it will spit some more interesting details. So this data, this tracing, I think is very important. So let's say a customer came up to you one day and said, "Hey, Adil, I read this application. It runs pretty well 90% of the times, but every 10% of the time it takes like 100 milliseconds. So I go back and see, oh my God, I don't see any issues. My application on my server side, it's all pretty cool. So I ask him to give me some more details, give me some request IDs. So when he gives me request IDs, I can go back in the server and try to find out which server served that request, and for that details, try to see whether a GC event happened at that time or not. So if a GC event happened, which most likely it would have, I can simply say, hey, that's nothing in my control. This is GC, bear with it. So another interesting parameter is the Go max proc. This sets the number of processes, number of CPUs that the Go application, Go runtime can use to schedule the core routines. But this is not. This was highly recommended setting until 1.5. But 1.5 and 1.6, you don't need to specify this setting. But if you're using Go 1.0 or 2 or 3, this is set to 1 by default. So I'm going to skip over this slide, but I can talk about that if there's more time. I'll leave this slide here for your reference. This I'll copy from there. In summary, I think be judicious in using objects. It's not free, as it appears like. You will have to pay the price somewhere down the line. Replace complex data structures like map with the simpler ones, where and try to see if you can cache the data or reuse the objects somehow. And also see if you can measure latencies in percentiles, because you don't want to screw up the customers which are like 5% or 1%. I think those are the customers which are going to write a blog post, say, hey, I opened Dropbox one day and it sucked pretty bad. So those are the 1% customers that you want to tackle, that you can only see with percentiles, not with averages. For all the Go 1.3 users, I would encourage you to upgrade. You would see a lot of performance gain in terms of GC utilization. And play with code GC parameter. Start with 100, tune it up to 200 and see how your heap size increases. And there are some links and further reading. Any questions at this point?
What kind of improvements would you like to see from the GC? Like lower pauses, what kind of things could be better? Not just the GC, but code performance in general.
So, like string manipulation is what I've seen.
Can you repeat the question?
So the question is that what are the other sort of changes you can make to improve GC in the code, right?
No. What would you like to? Is there any changes to the Go language itself that you would wish could be done to the language in the future, so that you would have better tools or more performance? Is there anything that you're disappointed with the language at the moment? You yourself?
Well, sorry, this slide, Go doesn't let me tune the GC at the level that I want it to, and at times I think I know if I give more threads or more CPU to the GC, that it will get faster, get it done faster. But I think somehow it looks like that's the decision that the Go authors or the inventors make, that we don't want to expose that part to the ordinary user. I think if you expose a little bit more GC tuning parameters out, like selection of what kind of GC you want to use. You want to use a CMS. You want to use a young GC better. You want to use generational GCs. So that kind of thing. But I think GC tuning could be improved a little bit more. But in general, in code, I've seen that the string manipulation, you can always find issues there.
So I'm curious, when you were talking about sometimes finding the need for some finer tuning. I come from primarily Java background, so we run into a lot of situations where we have to tell it to garbage collect early so we don't hit our heads or something, and this has to do with generational stuff. Have you run into issues with Go where it runs into a catastrophic problem because you aren't able to, catastrophic garbage collection problem, like in your production systems? I'm just curious if you run into something like that.
So the question is if we run into garbage collection issues in production?
Yeah, primarily driving from garbage collection that, in Java, I would know how to tune my way out of, potentially, and then you didn't have those knobs. I'm just curious, because maybe it just doesn't have those problems. It'd be great. I'm just curious what you found.
So we found that we do have issues in the tail latencies, and it is hard to debug. It is hard to point that what is causing that latency issue. Unless you have this GC trace enabled, I don't think we can say that for sure that request took more time because of GC. So the conjunction with this GC trace and profiling, we can answer the question. But yeah, if that issue becomes very serious, we would start getting more and more profiler logs to analyze what code path is not performant, and we can rewrite some small sections. So we have seen issues and we have dealt with them.
And then you've addressed it with
there's not a lot of tuning you can do.
Thank you.
Okay, thank you very much. One last comment. The session the code session I had earlier, that is all mentioned in a Go profiling log. It was written by Russ Cox, who was one of the guy who works at.
No relation.
No, not his brother or his family. So he works at Google and he wrote that blog post. So I kind of replicated what he did in the session. It's all documented. You can see the commands and all those things. You don't need to type in my commands. So thanks.